To get started with our calculus class, we're going to start with a review of functions and an overview of some algebraic concepts that will make class a lot easier. We're going to look at a few graphs to get started. This is a third-degree polynomial, and we'll get into those details a little bit later on in the course. This is a second-degree polynomial, and this is not like these other two in some way. What we want to know is try and figure out if these are functions. If I want to figure out if something is a function, one of the easiest things that I can do is I can run the vertical line test. And basically what the vertical line test is checking to see is if each x value has a unique y value. And when we say a unique, we mean only one unique y value. So as we run through these, and I run my vertical line test over the top of these, we can see for this value of x, there's only one y. For this value of x, there's only one y. And it only passes through one point on the graph. So yes, this is a function. On our second graph here, we can run the vertical line test as well, and we can see that it only passes through one spot on the graph. And again, this only touches one spot on my graph, so yes, this is a function too. My last one, as I run my vertical line test, you can see how it's different. I hit 2 points on my graph. So what is happening here is for this value of x right here, you can see that I have two values of y. I don't have one unique y. So no, this is not equal to a function. Now, functions have a lot of nice characteristics we like to work with, so that's why we're usually trying to be on the lookout for a function. Now, when we're also working with functions, we like to be able to talk about things like evaluating a function and also talking about its domain and range. So let's go ahead and look at evaluating a function first. Evaluating a function just means I'm plugging a number in to the function for the variable. So for instance, we could look at a function like f of x equal, let's say, 2 over x squared minus 1. Let's go ahead and start by evaluating this function for f of 3. So that means everywhere that there's an x, I will plug in a 3, and that corresponds right up here. Now what I usually do is wherever I have a variable, I go ahead and put up my parentheses, and I put out the framework for this entire function, and then just put parentheses wherever it is I need to plug in. So in place of x, this says that I should plug in a 3. So I'll plug in a 3. Now as I simplify this, in my numerator I have a 2, 3 squared is 9, 9 minus 1 is 8, and 2 eighths reduces to 1/4. So this is an example of evaluating a function. Let's look at another one. Let's go ahead and evaluate f of negative 3. Again, I'm going to do the same thing again. I'm going to set up my framework. I'm going to put parentheses wherever I see a variable x and go ahead and plug in a negative 3. Now you'd think you get a different solution here, but what's a negative 3 times negative 3? A negative times a negative is a positive, so I get a positive 9. 2 over 8 is 1/4. So that simplifies nicely. Now I want to go ahead and take a quick note over here. This is a very important idea. Negative 3 squared does not equal negative 3 quantity squared. What I have here on the right hand side of my base is negative 3. Over here on my left hand side, the base is just a 3. And then I square the base and then I negate it. So this one would be a negative, and then I would take 3 squared would be another way to look at that. Now over here, negative 3 quantity squared means negative 3 times negative 3, which is positive 9. 3 squared, 3 times 3 is 9. So I get negative 9, and of course that does not equal 9. So it's important to note the difference here. That's why I always put parentheses around my base so I evaluate these correctly. I can also plug in different variables. So for instance, I could plug in f of y cubed. So I'm going to set it up the same way. I'm going to set up my framework, and then I'll look at here and say, okay, everywhere there's an x in my original, I'll plug in a y cubed, so that'll go right here. Now as I'm rewriting this, y cubed squared, okay, y cubed squared, that means to take y cubed and multiply it by itself. Now if you know your shortcut rules for your exponents, y cubed times y cubed is y to the 6th. So I end up with 2 over y to the 6th minus 1. Now if you don't remember your shortcut rules for exponents, you can write these out. Y cubed quantity squared would be y cubed times y cubed. And then of course y cubed would be y times y times y. This other y cubed would be y times y times y, which of course is y to the 6th. Shortcut rules are easier to remember if you use them a lot. So go ahead and look at those y cubed quantity squared. When you raise a power to a power, you multiply the powers. And we use these ideas a lot in calculus, so it's important to know your rules of exponents. Sometimes you'll be asked to simplify an expression using functions as well and into something called the difference quotient. The difference quotient is showing up a lot, and we'll be using it in the next sections as well when we start talking about derivatives. But let's go ahead and write what the difference quotient is. The difference quotient is the expression f of x plus h minus f of x all over h. And again, we'll be using this idea a lot, but we're going to be using this to evaluate at different function values. So let's evaluate the function, or let's say simplify instead. Simplify the difference quotient for f of x equal, let's say, 4x minus 2. Okay, so the difference quotient again was f of x plus h minus f of x all over h. So when we're working with something like this, it basically says f of x plus h means to come up here, and everywhere that I see an x, I'm going to put in my x plus h. So this is f of x plus h. Now my minus sign comes from my original expression. I need to make sure I put up a set of curly braces because I'm going to be subtracting off a difference here, and if I don't have the curly braces up, what ends up happening is the negative sign doesn't get distributed correctly. So again, I have 4, set up my parentheses for my variable. Now this says everywhere I have an x, I plug in an x, so that one's not so complicated. And this is all over h, and that comes directly from here. So this piece is just my f of x. And being able to work with the difference quotient is going to be really important. So what we'll do to get started here is we'll distribute the 4. So I'll have 4x plus 4h minus 2. That comes from here. And then I'm going to take this negative and I'm going to distribute it. We'll distribute to the first and second part here. So I'll have a minus 4x plus 2 all over h. Now when you're working with the difference quotient, you're going to see something kind of interesting happen here. The negative 2 and the positive 2 cancel. The 4x and the negative 4x cancel. And basically all I'm left with here is 4h over h. And the h's cancel. So I'm left with a 4. That's simplified completely. I have to distribute combine-like terms very carefully. Now the pitfalls to watch out for: after the minus sign, make sure you put up your curly braces to make sure the entire expression has the negation distributed through to it. So that's a big important idea. So this is an example of simplifying with the difference quotient, and you'll be simplifying with other functions as well, but the difference function does come up quite a bit in calculus. The next thing that we're going to be looking at is a composite function and the idea of a composite function. Now composite functions have a special notation. F of g of x. So this is a hollow dot in here, or a hollow circle that means of. This means to take the function g and plug it into the function f. We could also have an expression like g of f of x. So that's going to look like take the function f and plug it into the function g. So you always start with what's closest to the x, and you plug first into that and then to the next. Okay, you could also have something like g of x. That means you take the function g and plug it into itself, and we'll look at some examples here. And of course we could also have f of x. Now I only have 2 functions that I'm working with here, but I could have 3 or 4 functions as well. So for an example, let's look at f of x equals the square root of x. And let's look at g of x equals, let's say, x squared plus 3. So let's go ahead and start looking at all 4 of these different composites that we can here. So let's look at f of g of x. So f of g of x. So that means I take the function g and I plug it into f. So the function g is x squared plus 3. The function f, remember, is just the square root of x. Now let's recall what happens here. I just have a square root sign that's f, and then everywhere I see an x, I plug in x squared plus 3. So again, I plug one into the other. So if this is f of x and this is g of x, this is f of g of x. So we're working down. Let's go ahead and look at g of f of x. G of f of x. So that means I take the function f and I plug it into g. But f is the square root of x. And remember, my original function g is x squared plus 3. So again, that's something squared, my variable squared plus 3. Now in place of that x in my function, I'm going to plug in my argument here, which is the square root of x. So I get the square root of x squared plus 3. Now the square root of x squared, that cancels, and I'm just going to be left with x plus 3. Because again, the square root and the quantity squared cancel. Let's go ahead and look at g of x next. So g of x. This means for my function g, I'm going to plug in my function g, x squared plus 3. So as I'm working here, and I plug in, I'm going to have something squared plus 3. Now that something that I'm going to plug in is the function itself. So this would be an example of a composite function. Now if I want to, I could distribute the squared, or sorry, not distribute, I could actually FOIL this out and combine like terms and simplify, but I'm just going to leave it in this form so we see where the function itself came from. We could also look at f of g, or sorry, f of x. And in my original function f, I'll plug in the function itself, which is the square root of x. So remember, the function f was the square root, and then I'm going to plug the square root of x directly in. So basically we're taking the square root of x twice here. So that's the idea of composite functions. And we can do quite a few different things with composite functions, and we can simplify quite a few different ways with composite functions. But the idea is to be able to look at a graph and to work with it by plugging in one value into the next. Now sometimes instead of being given the original functions, you'll be given the solution or the composition and then asked to work backward to figure out where the functions came from. So for instance, let's say I have h of x, which is f of g of x. So this means I took my original function f and I plugged in my function g. And when I did that, let's say we got something like x to the 4th minus 2 quantity cubed. So what did I plug in to f? Well, if I look at the outside of this function, this just looks like something cubed. So if I called f of x just something cubed, that would take care of kind of the out part of this. Now the inside part of this would be what I plugged in, which was x to the 4th minus 2. So if I composite these again in this order, f of g of x, I would get this original function back. So it's important to be able to look at these forward and backward while you're working. Another important idea is to be able to work with the domain and the range of a function. So when we get started talking about domain and range, it's nice to be able to look at a graph first. And we will look at a graph in just a second, but let's go ahead and define what those are first. So these are big ideas, domain and range. Domain is horizontal movement, meaning what's going on with my x-axis, so what are my possible values of x. And then my range are my y values. So my range are my possible y values. Now sometimes I don't have a function with x and y. Sometimes I have z and q or something like that. So not just x is the only variable that I can look at here. It actually depends on the context of the problem. So this is called my independent variable. I'm not sure why that marker got so big. Let's make it smaller. So this is my independent variable. And it's also known as my input into the function. Now when I talk about the input, it means what value do I plug in, and then after I plug that value in, what is the value that comes back out of it? So over here, then, this would be my dependent variable. And my output. And so let's look at a couple different examples here. So for our first example, we're talking about, let's say, the volume of a cylindrical water tower. So first of all, use your imagination a little bit here for my drawing. So this is a cylindrical water tower. Now, the cylindrical water tower, for my example, has a radius equal to 15 meters. And its total height is 55 meters. So from top to bottom, it's 55 meters. Now, the volume for this is going to be pi r squared, which is the circle, the area of a circle, times the height. So it'd be like stacking the circles. So volume equals pi r squared h. Well, what I want to do is I want to take this idea and I want to say, okay, I want to create a function that would give me the volume if I just filled this up to a particular height. Now remember, 55 meters is my height, so h equals 55 meters. So if we took the same picture and then I started talking about filling it up to different heights, I could create a function. So it's the same picture, and let's say I only want to fill it up as high as this right here. So I'm going to only fill it up to here, and so this is my new value of h from here to here. Well, what the function would look like then is v equal pi. Now the radius hasn't changed, it's still 15 h. So pi times 15 squared h. Now this h can move, it's variable, it could go higher or lower. And I just want to write this generic formula. 15 squared is 225. So this is 225 pi h. So this is my function that I'm working with here. Now usually when we start talking about the function, I might put this in functional notation. Instead of v, I might put v of h and say, you know what, this depends on height. So volume is dependent on height. So now when I start talking about my independent and my dependent variables, let's refer back to domain. Remember, domain is my horizontal. In this case, I don't have an x. I don't have a y, so it's not as obvious what to do here. But this is my independent variable. So my independent variable in this particular case would be h, height. Now my range which I don't really need to talk so much about here because I want to talk more about the domain. This is my dependent variable. Again, it's our vertical value. Now our vertical, I shouldn't say vertical in terms of vertical in the picture, but if you were to plot the height versus the volume, that would give us that idea. So it's my dependent variable, which in this case is going to be v of h. Okay, this is also known as my input, and my range, which is my dependent variable, is also known as my output. So as I'm working through all of this, the conclusion I come up with is volume is dependent on the height, or how high I fill the water tank. So volume is dependent on height. So they want us to figure out a domain here. Well, I could fill the tank all the way to the top or not put any water in at all. So when I start talking about that domain, the domain is going to start talking about how high I can fill the water. Well, it could be 0, and it could go all the way up to 55 meters. So the way I'd represent that is 0, 55. Now this is called interval notation. And interval notation basically includes every single number between 0 and 55. That's what we have here. Now I use a bracket because a bracket means equal. If I use a parenthesis, it means it gets really, really close to the value but never quite touches it. So this is an example of being able to find the domain of this function. Now finding the range, what I could do is plug 0 in and then plug in 55, and that would give me my range of values as well. Now another way that we can find, besides just kind of logicking our way through this to find the domain and the range, is to actually do a graph. So next one, let's go ahead and look at a graph of a function and identify its domain and range from the picture. So let's go ahead and graph a function. Let's graph the function, let's do g of x equals x plus 1 over x squared minus 2x minus 15. Now there's a lot of different ways that we can graph this. We're going to graph this using a graphing utility. Now on your exams you will not have access to a calculator. We will have a bit of a note card that we'll discuss later, but we don't want to get dependent on the use of calculators. If we do use these for homeworks and quizzes and your written homeworks or your handwritten homeworks, that's okay to check your work, but don't get dependent on it for doing your work. So let's look at the graph of x plus 1 over x squared minus 2x. Now I already have this in, so I'm going to start over so you can see where that came from. So again, x plus 1 over x squared minus 2x minus 15. I'm using a TI-84 Plus. If you're using a different type of calculator, like a Casio or some other model, you might have to Google how to do some of these steps. If you're using a TI-84, some of you have a shortcut key for a fraction. It's called alpha y equal. And then if you can see here, I have numerator over denominator. And then I could just go ahead and put my function in. I'm going to assume that not everybody has that, and I'll show how to enter this function otherwise. I need to have parentheses around my numerator and denominator. This is my variable piece right here. So x plus 1. And even if my variable is, let's say, z, I can still use x when I'm graphing. And again, I need a parenthesis to open the denominator, and I need to have the entire denominator in parentheses. So that's x squared minus 2x minus 15. Close parenthesis. And then we'll hit graph. Now sometimes you have to adjust the graph, and this is not a splendid picture of this. Doesn't look too great. So what I did is I changed the version of my calculator to a TI-84 Plus CE so we can see a little bit more what's going on here. So this looks a lot better. I'm going to snip this and put it into our lecture, and then we'll talk about it a little bit. Now there's a lot of very nice online graphing options as well. So one of them is called Desmos, and again, you won't have access to Desmos on an exam, but it's a good way to check and to look at your homeworks and quizzes and your handwritten homework as well. So I'll show you what Desmos looks like. This is an example of Desmos. You can see up here it says desmos.com. And you can see that I plugged in the same function and I have a nice little picture here. Getting used to using Desmos is pretty straightforward. It's a nice little graphing feature to use to check your work. Again, not to do your work, but to check your work. So I'll pop this one in as well, just to use as a comparison. Some others are Mathway and Wolfram Alpha to do some graphing and to also be able to check all sorts of other types of work. So I recommend, again, that you use those to check your work, especially on quizzes, because a lot of times on the quizzes you have to redo the whole quiz even if you only miss a couple problems. So it's a good idea to check them before you submit it. Okay, so here's a couple graphs. It's the exact same graph. If you notice on the left-hand graph from our TI calculator, this graph actually extends up, and this one does as well. This one extends up, it's implied, and this one extends down. And the arrows are the same on all of these. Okay, so these are implied that they keep traveling in the same direction. Now we want to find the domain here. Now easily we can see that the domain in this case is that horizontal movement. So the domain would be all my x values that are covered. So if I look at all my x values, I can see that they travel from negative infinity, and then right here though it kind of stops. This is called a vertical asymptote. It's this dotted line. Now it looks like this is crossing, but it's actually just getting really, really close, never quite crossing. And I can see that I have another one here. So this is x equal -3, and this is x equal 5. These dotted lines are. So what I have here, I have vertical asymptotes at x equal -3 and 5. Vertical asymptotes are these dotted lines that you never cross. The graph never crosses these. It gets closer and closer to these, but never quite crosses these. And so for this particular case, for my domain, I can see pretty clearly here that x can be anything except -3 and 5. So that's an easy way to say the domain. Now there's other notations. There's set builder notation and interval notation. But for now, we'll just say, you know what? It looks like to me x is everything except -3 and 5. I can also talk about the range. Now range is vertical. You can see that everything is covered on the y-axis. It kind of looks like something's going on right in here. Maybe there's a gap, but when I trace it back to the y-axis, you can see that the y-axis is covered. So I would say that my range is all real numbers. There's no gaps or jumps vertically. Now, how did I find these places where this is not equal to -3 and 5? Well, I can come over here as well, 1, 2, 3, 4, 5, and I can see that gap appears here. And the yellow doesn't show up very well. And I can also see this gap right here at -3. Well, where that came from, I'm going to call vertical asymptotes VA, is I take the denominator and I say, you know what? The denominator can never equal 0. So I take x squared minus 2x minus 15, and I say, you know what? It can't equal 0. And then you factor it, and I end up with x minus 5, x plus 3 cannot equal 0. And if I add 5 to both sides here, I get x cannot equal 5. And if I subtract 3, I get x cannot equal -3. So that vertical asymptote comes from the fact that the denominator can never equal 0. So vertical asymptote is a very big idea here. Again, this was used graphing my TI. This was used using Desmos. And again, these are ways to check your work, not do your work. So don't get in the habit of depending on these. So we've talked about the domain and the range. We've talked about graphing. We've talked about being able to look at dependent and independent variables as well. The last thing that we're going to talk about are even and odd functions and symmetry. Let's first of all talk about types of symmetry. We have three different types of symmetry that we like to look at. We have symmetry about the y-axis. And then of course we have the x-axis as well, but let's go ahead and focus on the y-axis first. If we have symmetry about the y-axis, basically if I folded the graph on the y-axis, I would have perfect symmetry, or I would have a perfect match. So let's go ahead and look at symmetry with respect to the y-axis. Now some of these, because I'm sketching them, aren't going to be perfect, but we'll try for the best. So if I look at this graph, remember this is my y-axis. If I folded this graph over onto itself, it would be the exact same points. Well, when I talk about symmetry with respect to the y-axis, what ends up happening is I have an ordered pair xy. I have a reflective ordered pair over here of negative xy. So notice when I'm symmetric about the y-axis, the y's stay the same and the x's just negate, and I can show that that's true. Let's go ahead and look at symmetry about the x-axis. Now when I talk about symmetry about the x-axis, it'll kind of be a little similar, but instead of being able to fold this over on the vertical or the y-axis, I'm going to be folding this across the x-axis. So an example of that would be a parabola not opening up like our other one, but perhaps a parabola opening on its side. So what ends up happening here, for this reflective point xy, I have the reflective point down here that the x value is the same, but the y value is negated. So this is symmetry about the x-axis. If I folded this part up across the x-axis, I'd have an exact match. Now the last type of symmetry that we like to talk about is symmetry about the origin. And sometimes this is the harder one to see. It's definitely the harder one to draw as well. So symmetry about the origin. Now this example is symmetric about the origin. Now when I talk about symmetric about the origin, it's not as obvious to see. But what ends up happening here is if I have an ordered pair, let's say xy, I have a mirror image of that ordered pair down here at negative x, negative y. Now another interesting thing about origin symmetric or about the origin is I have this line. This is called the y equal x line, and this is the line that I'm symmetric about when I'm talking about the origin. It goes right through the origin. That's how that comes into play. So if I have a value xy, if it's symmetric about the origin, then if I have to have the concluding value of negative x, negative y, that should match. So again, these are not as easy to see when I'm talking about symmetry about the origin. Now I can also talk about even and odd functions quickly. First of all, let's talk about an even function. Now we're not just looking at the numbers in the function. I'm not saying that all the numbers are even or all the numbers are odd or something like that. But basically with an even function, for f of negative x, so that means if I evaluate my function at negative x, I get the exact same value as if I evaluate my function at a positive x. And we'll look at some examples of that in a minute. Now, if I talk about an even function, the graph of an even function is symmetric about the y-axis. So an even function has y-axis symmetry. Now I can also talk about an odd function. So for an odd function, what ends up happening here is if I evaluate a function in negative x, I'll get the exact same thing as if I evaluated it at an x and negate it. Now this doesn't have y-axis symmetry. This has symmetry about the origin. So these are some important characteristics to know. Now, everything that we've looked at so far is kind of theoretical. So the next part that we're going to look at is actually working with some problems with even and odd functions and their symmetry. So for this example, let's determine if the function, let's say f of x equals x to the fourth minus 3x squared plus 8 is, let's do even, odd, or neither, and its type of symmetry, if any. So we could go after symmetry first, or we could go after the even, odd business first. Doesn't matter. I'm going to go ahead and look at, first of all, whether it's an even function. So I'm going to check to see if it's even. Now remember, for an even function, if you come and look right up here, if it's an even function, f of negative x equals f of x. So f of negative x equals f of x. So we know what f of x equals already. That was x to the fourth minus 3x squared plus 8. Now let's see what f of negative x is. So that means a negative x quantity to the fourth minus 3 negative x quantity squared plus 8. Now remember, it's important to have these parentheses here, because without these parentheses I'd only be squaring the x and not the negative, or taking the x to the fourth power, not the negative. Well, a negative to the fourth power would be a positive, so this would equal x to the fourth minus 3x squared, because a negative x times a negative x is a positive x squared plus 8. And we're checking to see, does this equal, that's our question, does this equal x to the fourth minus 3x squared plus 8? And it does equal. These are identical, so therefore f of x is an even function. And if it's an even function, what ends up happening then is we also know it's symmetry. So it's symmetric about the y-axis. So it has y-axis symmetry by default then. So these are pretty straightforward to go in and check. You just really need to make sure that you're putting parentheses around the base of those exponents, because that can really throw you. Now there's a few other little things that we talk about when we're talking about even and odd functions, and I'll just kind of give you a short rundown here. Some problems that you'll see show up in my math lab when you're doing your homework. This says, you know, what happens if you add an even and an odd function, or what happens if you multiply them? What type of symmetry do they have? Well, let's go ahead and run through these real quick. So if I have an even plus an odd function, what ends up here is I have no symmetry. So again, an even function had y-axis symmetry, an odd function has origin symmetry, but when I combine them, they have no symmetry at all. Let's go ahead and look at what would happen if we multiplied. What if we had an even times an odd? If I took an even function times an odd function, I would have origin symmetry. And we can also talk about composites of these. What if I had even plugged into an odd? Or what if I had an odd plugged into or composited with an even? Let's go ahead and look at our first option. An even composited with an odd would be symmetry about the x-axis. So I guess I'll write that x-axis symmetry. So if I took an odd function, I plugged it into an even function, I'd end up with x-axis symmetry. Now, if I took an even function down here and plugged it into the odd function, I'd end up with y-axis symmetry. Now these are interesting characteristics of even and odd functions and the symmetry of them. These types of things are not crucial to memorize for an exam, but they will be helpful to do or to know for your homework. Now to get started with your first homework set, go ahead and log into my math lab. You'll have a syllabus quiz that if you haven't taken that you'll need to take before you get started with your homework. And then once you get started with your homework, remember you have to get a 90% or higher before you can go on to the corresponding next homework or quiz. Another thing to keep in mind is while you're working in the My Math Lab, there's a Help Me Solve This. There's also a Show Me an Example. There's also a Connect to the Tutor option, connecting to the Pearson Tutor. And then also remember I have my online office hours, and you can also take a screenshot with your phone and text that to me as well with the texting service if you have questions. So there's a lot of ways to get help in class, so if you're stuck on anything, please feel free to speak up right away and let me know how I can help. Good luck this semester and good luck with this homework set. As usual, if you have questions, please let me know.